Hi everyone, my name is Riya Joshi, and in this video I will explain PCA from scratch. So most people say PCA reduces dimension, which is very true, but it is the end result of the PCA, not actually a PCA. PCA actually rotates your coordinate system, so the first new axis capture the maximum variance, the biggest spread of our data. And why PCA choose variance, not any other statistical method? Because if you calculate the mean of these two data points, you will get the same exact mean, which does not differentiate your data points, which is far very different. -5, 5, and -10, 10 are very different from each other. So it will, the essence of the data and the idea how much it is spread, it's captured by the variance. And the plus point is variance is the square function, so it is a lot easier to differentiate it, and we will use it as an optimization problem later on. So here this variance will help us. And if you say that why we didn't use mean absolute deviation, so it is also not a differentiable function. Now the next thing is that PCA actually uses 5 steps. The very first step is the standardization and the centering data. Centering is nothing but you just center the mean of the data at the origin, and in the standardization you just scales all the variables. The second step is the covariance metric computation. Now variance doesn't tells you the orientation of the data, but covariance actually tells you the relationship between the axes, so it gives you the orientation of the data. So covariance, this is the covariance matrix for the 3D data. So it actually have the variance also, because covariance of xx is nothing but the variance of the x. So here it is the variance of x, variance of y, variance of z. So it actually calculates the variance in all the x, y, z directions, and the covariance tells you the orientation of the data. So here is our covariance matrix. Now the third step is the eigen decomposition. And when you do the eigen decomposition, because actually what you want, what you really want in the eigen decomposition, that we want to find a vector u that maximizes the variance of our projected data. So as you derive all these things, so you will get the total variance equals to ut. This is the covariance matrix S. You can denote it as a S, and this is U. So this is the total variance, and now we want to maximize it. And to doing the maximization of this, we use some Rayleigh quotient equation, which at the end gives you the result that the largest eigenvector of the covariance matrix always point into the direction of the largest variance of the data. And that is very, very true. And to find the maximum direction without making the vector infinitely long, that u making this u infinitely long, we use a Lagrange multiplier, which leads us to the eigenvalue equation. And here is all the proof that the direction of maximum variance must be an eigenvector. We can compute this by applying the Lagrange multipliers. Here is all the definition. I have some time constraints, so I'm not going to explain this. Now the last step is just the projection and the selection. So finally we pick the top k eigenvectors to reduces our dimension. We project our original data onto these new axes, and then we have effectively rotated our world to look at the data from its most information angle, throwing away the noise of the low variance axis. So it's all about the PK. Thank you.